This is the lecture on how to do the ANOVA in R. So if you come to modules under iLearn, week 9, these are the lecture slides that we'll be using, and these are this is the R code that we'll use, so you want to download that. And then the other one is a data set that we're going to use. So this is nationally representative survey data. So you'll want to have both of those available. So we'll call this data set D1. That's consistent with what we've done so far in the class. Okay, so the question is like, when do you use an analysis of variance or an ANOVA? Last time we talked about the t-test, right? If you have two groups and you want to compare the means between the two groups, you want to know if one group is statistically different from another group, that's when you use a t-test. But a t-test can only be used with two groups. Well, what if you have more than two groups? What if you want to know if there are racial differences and there's more than one race category? Or what if you want to know if there's gender differences and you have more than two gender categories? And honestly, most things we have more than two categories that we're dealing with. So Fisher is the person who came up with the ANOVA test, and so the test statistic is called the F test. So here's the little chart that we use that kind of gets us there. Are you examining the relationships between variables or the differences between groups? We're examining the differences between groups. Is it the same person more than once? No. How many groups are you dealing with? More than two groups. How many factors? Just the one. So we use a simple analysis of variance. So it's just like the t-test, only you have more than two groups. And of course, the math behind it is different. I don't go into the math behind statistical tests in this class, but the math is different. But for practical purposes, it's just like a t-test, but you have more than two groups. This is something I like to point out. There's a lot of like math calculations that go into things, but ultimately you're going to be comparing your F statistic to the critical value of some kind. And ultimately, the F statistic is calculated by taking the mean of squares between groups divided by the mean of squares within groups. What this means is that if you have not a lot of variation within your groups, then a smaller value here makes a difference here larger for the F statistic. So oftentimes you'll have studies that are done on college undergraduates. And college undergraduates are more similar to each other than the general population is similar to each other. So when you do these samples with college students, you typically have a lower mean squares within groups than you might find in the population, which makes it so that smaller differences between groups can give you a statistically significant F statistic. So for most of you, that's not going to matter much in your lives, but I just pointed out because from time to time, I think it's good to think critically about what we know and what we don't know and how the samples we use influence what we know. And so sample selection influences more than just whether something can be generalized to the population. Sometimes a sample can minimize the denominator in your test statistic, which will inflate those values and make it more likely to reject a null hypothesis. So there's 2 degrees of freedom in the F test. You've got the number of groups minus 1, and then the number of groups minus, then the number of groups minus the sample size, So depending on the number of groups, right, number of groups minus 1, number of groups minus the sample size, those are your 2 degrees of freedom. So let's say that I had, well, so this is not 5, I only have 3 here, but whatever. Let's say that I got high school scores, language scores for high schools. They took some test, and I want to compare the schools to each other, like who does better on average at language tests. So I've got group 1, right, high school 1, high school 2, high school 3, and then I've got their language scores each year. So the null hypothesis is that there's no difference in the population means between those schools. If the schools are no different than each other, their means should all be equal to each other. The research hypothesis is that the sample mean for the groups are not equal to each other. any of them could be different, right? These two could be equal to each other and have this one be different, and I would still reject the null hypothesis. So that's the idea, right? The means are all equal to each other. Alternative, they're not all equal to each other. We choose our level of risk, 0.05 is what we typically choose as our alpha. We choose the appropriate test statistic. Since we're learning about how to do the F test or the ANOVA, we'll choose the F. Then I compute my F. Then I go to this website or some other place and find the critical values of the, oh, that website doesn't work. Well, we'll just Google it. I find the critical value of the F statistic, right? So I'll go over here and I'll go Daniels, Oper. I'm sure it's in here somewhere. Yeah, just needs a new, he has a new link or whatever. Okay, so I have 3 groups over a 9-year period of time. So I should have 9 observations. So I'm going to go degrees of freedom. 3 minus 1 is 2. And then 30 minus 3 is 27. So I calculate my critical value, and it's 3.35. So if my F is larger than 3.35, I'll reject the null hypothesis. So this is like an example of all the calculations, if you were to do it by hand, like how you would calculate the various things to conduct the ANOVA test. I used to make students do this, but I realized they were just getting confused and it wasn't helping them understand the concepts that are important. So I don't make you do it by hand anymore. But in the end, you come up with an F that's 8.799, which is bigger than 3.35. So I reject the null hypothesis, and I conclude that these groups are not all equal to each other. One of them is different. Which one is different? Well, I mean, I guess I could eyeball it and sort of see that this one seems different than this one. With the ANOVA test, it won't actually tell you which one's different. It's an omnibus test. So you have to calculate a follow-up test to figure out where the difference is. I'll show you how to do that. But first, I want to make sure that you understand how to do the ANOVA test in R by yourself. So when to use an ANOVA test, like in terms of like being practical and thinking about how to make it work, your dependent variable has to be a number, and theoretically it should be normally distributed. It should be continuous, have lots of values. And also your independent variable should be a category with more than 2 options in that category. So if all you have is like yes, no, you could do an ANOVA, but you don't need to. You could do a t-test, right? But if what you have is race and you've got multiple racial options, or it's income and you've got income categories, or it's age categories, then you do an ANOVA. I think ANOVAs work best when you're analyzing an experiment of some kind, when people are randomly assigned to those different experiment conditions. So I'll use that as an example. So in 2013, I did a national survey, and people were randomly assigned to an experimental treatment group. They were taking the survey, and they were randomly assigned to see one question instead of another question. So here's how the experiment worked. I said, imagine that A, and then I filled in the blank. So they were either assigned to see a Hispanic acquaintance, or an obese acquaintance, or an openly gay acquaintance. They don't know what the other options are. They just see one of those options. So I had the survey randomly assign people to having this blank filled in with one of these 4 options, and that's all they saw. So let's just say you were in the atheist treatment group. Imagine that an atheist acquaintance came to you and asked you for help with each of the following activities. How likely would you be to help them on a scale from 1 to 10? So my dependent variable is a number that goes from 1 to 10. My independent variable is going to be which of these words was randomly assigned into that blank right there. So the idea is that it lets us see if there's some kind of bias, right? At the time, it was against the law for same-sex couples to legally marry, for them to marry. So I have in here obtain a marriage license, right? So you would say, well, maybe people didn't want to help an openly gay person obtain a marriage license because that's illegal. My my hypothesis in this project really had nothing to do with gay marriage or same-sex marriage. It was all about bias against atheists in America. So, so you might see some differences with like a gay person. Oh, I don't want to help them get a marriage license, right? But why would there be a bias against helping a Hispanic or an obese person get married? Or register to vote, right? That was an option that maybe we could see some bias in there. So the first thing I like to do is do a little box plot. I'll just do this in R. So here's my code. I'm going to read in that attribution ANOVA data. So I've got 1,800 observations of 11 variables. Okay, so the first thing I want to point out is that an ANOVA looks at the means by groups. And it just tells you if one group is different than other groups. In this data set, I have some missing values. I'm just going to do a summary of this dependent variable we're going to do. I'll just do a summary of the whole data set. It'll make it easier. Okay. So this is the dependent variable that we want to use. This is the treatment group. This is our independent variable, right? So I've got people that were assigned to the openly gay category. Sorry, I forgot you guys can't. Let me get this thing so you can. Okay, right here. 411 people in that group, 411 in that, 412, 409. But you see this? 157 missing values. So when I do the statistical test, this is going to show up as a missing value, as a category. And guess what? The mean on this is going to be 0. So if I'm doing a statistical test where I'm comparing the differences of means between groups, and this group has a mean of 0, it's going to be statistically significant for sure, because this missing values group all has the same value, and it's just going to be statistically significant. So I need to get rid of that. So that's what this code up here does. This says, create a new data set, call it D1, and what it's going to be is get rid of all the missing values from D1. So watch over here what happens when I run this code right here. See how now it's dropped down to 1,588 observations. And now if I do a summary of that data set again, all those missing values are gone, and there were some other missing values that were deleted. So that got rid of all the missing values, but this category is still here. So when I run the analysis, I'm still going to have this category with these with all these missing values in it, and it's going to mess it up again. So then the other thing I have to do is, this says, get rid of categories with no values in it. It's called drop levels. So I say, create a data set D1, and it's going to get rid of all the missing categories in D1. So when I run that, you don't see anything over here because the missing values are gone. But now when I do that summary again, now I don't have that extra missing category. So you have to make sure you do that on your data before you run your models. Otherwise, you're going to get weird values, weird results. Okay. Also, some people don't like scientific notation. So if I run this, it makes the p-values look the way that people like to see the p-values look. Okay, so the first thing I'm going to do is I'm going to plot, do a box plot. And the code to create this box plot is right here. And as you recall, or maybe not, from early in the class, what a box plot tells you is these dark lines are the median scores for each group. Between 25 and 75% fit within the box plot part. And then these whiskers cover the rest. So what you see is, like in the openly gay category, the median is the same as in the Latino and almost the same as atheist. But you see how this box is larger down low. That means there were more people in this group that put values down here than there were that put values up here, right? So these two are pretty similar in their distribution, but this one has a lot more values down this way. So this is the median, remember, right? So the mean on this one's probably a little bit lower down. You see that obese has the highest median willingness to help their friend get a marriage license, right? So if if you're fat like me, people seem to be happy to try to help you get married. They're very excited. Somebody said yes, let's go help them get married. But you see at this time on Openly Gay, there were more people that were like hesitant about wanting to help their friend get a marriage license. So it looks like there's a difference, right? If I just eyeball that, I say, oh, those don't look like they're the same. But we want to do the statistical test to know statistically are they different. So our null hypothesis is that the means for all these groups are the same. Again, I don't see the means in this, I just see the medians. But the null is that the means are the same. The alternative is that the means are not all equal to each other. I choose my level of risk, 0.05. I choose the test statistic, which would be the F. And then here's how I run the code. Here's how I run the model in R. So I give it a name, mod.1. Once we get to this level of statistics, you need to give things names. You have to give these equations names so that you can find out everything you want to find out about them. If you just run the code like this, you're not going to get all of the answers I ask you questions about. So I give it a name called mod.1. You can call it anything you want. Equals AOV, that's the code telling R to run an ANOVA. This is my dependent variable, the marriage license, predicted by the treatment group that they're in, and then I have to tell it that the data equals D1. So when I run the critical value, we go back to, sorry, I'm gonna look in R. So I have 1,588 observations, and I've got 4 groups, right? So when I go to this website, wherever, here you go. So 4 groups minus 1 would be 3. 1588 minus 4 would be 1584. I calculate that, and I get an F critical value of 2.61. So when I run my test, if my F is larger than 2.61, I will reject the null hypothesis. So here's the output I get. I'll run it in R just so you can see that I do the same. So first I run the model. Nothing happens except for that the model shows up here. But then if I type in summary of mod.1, then it gives me this output right here. So there's my degrees of freedom, by the way. If I needed to, right, if you forget how to calculate the degrees of freedom, R gives it to you right there. You could just take those values, paste them into that website right there, and get your critical value. R is so very nice. Here's my F statistic, that's 10. 10 is bigger than 2.61, so I reject the null hypothesis. My p-value is 0.000, which is less than 0.05, so I reject the null hypothesis. Also at this stage, we're lucky because R is now putting stars in for us, and this tells us what those codes mean. So if you get nothing there, your p-value is like not at all significant. If you get a dot there, it means your p-value is less than 0.1. If you get 1 star, it means your p is less than 0.05. 2 is less than 0.01. 3 is less than 0.001, which is what we get there. So there's 3 ways you can tell if your test statistic is significant, right? There's 3 ways to know if you reject the null hypothesis. 1, compare the critical value to the test statistic. 2, compare the p-value to your alpha. 3, look for stars. If there are any stars, then it will tell you reject the null hypothesis. So stars, p-value, test statistic, they'll always tell you the exact same thing. And as we move forward in the course, we're going to do this more. So just kind of get, some people, all they remember is just look for stars. But there's 3 ways, but they'll always tell you the same answer. That's why people remember just look for stars, because they don't have to remember the other ways. But it's compare your test statistic to the critical value, compare your p-value to the alpha. If your p is less than the alpha, you reject. Or if there are any stars, you reject. Okay, so how do I know which group is different? This is why it's nice that I called the equation mod.1, because I can do this thing called Tukey HSD. So Tukey was a statistician. He came up with this test called the honestly significant difference. So this is the code. So if I type in Tukey HSD of mod.1, then I get this output. And I know this output looks scary to you, but I'll explain to you how to do it. So this is comparing groups to each other. So this is comparing the Latino group to the atheist group, the obese group to the atheist, the openly gay to the atheist, right? Tukey goes through and compares them all, one at a time, to see which one's different. Then it tells you here what the difference is, so you can know specifically how much it matters. And then it gives you a p-value, so you can tell if that difference is significant. So imagine how helpful this could be, like if you worked in, say, medicine, right? And you're trying to figure out what's the right dose of a vaccine to make sure that people don't get COVID-19, or what dose of remdesivir to give people on ventilators to help them come out of the ill effects of COVID-19, right? You could say this dose minus no dose, this dose compared to no dose, a higher dose compared to no dose. And you can see what the difference is between each of those, whether it helps or hurts, and by exactly how much it helps or hurts. And then, so then it's really helpful, right? So the first thing I do with this data is I look for the p-values. I look for p-values less than 0.05. If it's bigger than 0.05, like this one, this one, this one, it means the differences are not significant and we don't care. So I have openly gay compared to atheist is significant. Openly gay compared to Latino is significant. Openly gay compared to obese is significant. Then I look at the difference. So if a person in the openly gay treatment group, on that 10-point scale, they're 0.09 less likely, because it's negative, to help their gay friend get married compared to an atheist. And compared to Latino, it's 0.08 less likely to help an openly gay person. And on obese, it's 0.129 less likely. So the scale goes from 0 to 10, right? So we're not even talking like a whole point difference. We're talking about a 1/10 of a point difference. So it's significant, but the difference is small, right? So that's the idea of the Tukey HSD. It lets you see, oh, we're not stuck with, is it significant? Yes, it's significant, but we want to know how much it matters. And what we can say is, okay, if you're an atheist that wants to get married, your friends are going to be, just a little bit less likely. We could calculate that into percentages, right? But maybe that's like 1 or 2% less likely to help you vote, or help you get married than if you're an openly gay person is like 1 or 2% less likely to help you get married than if you're an atheist. So we can measure bias in that way, right? So how about mailing a package? That's a different variable. You just change it to MP instead of ML. Everything else should look the same. And I want to know, is there bias about mailing a package? Like, okay, fine. It was illegal to help a gay person get married in 2013. So maybe people were hesitant about that, but there's no laws about helping a person mail a package. So are there any differences in willingness to help their friend mail a package based on who they are? So the null is that the means are equal to each other. The alternative is that they're not equal. Our alpha is 0.05. Critical value is going to be the same, 2.61. The F is 10.23. Just to double check that, run the code. Yep, 10.23. Our p-value is 0.00. So what do we do with the null? We reject the null. Okay, so now we know there's a significant difference. So which of these groups are they more likely or less likely to help mail a package? Maybe it's like if your obese friend comes and says, hey, will you help me mail a package? You're like, well, you could probably use the exercise, pal. So maybe they say no. Well, let's find out. So if we look at the output from Tukey HSD, you see almost the exact same pattern as before, except for this time it's positive. Right, so what we see is that people are significantly more likely to help their gay friends mail packages. Although there's something about obese, right there. The difference is not as big here as with these other ones, but still, obese compared to Latino, obese compared to atheist, they're statistically the same, right? So for some reason, people are much more excited about helping their openly gay friends mail a package. So think about why that might be. I mean, I don't know because there's no way to test it, but my hypothesis of why that is because These are all set up on the same screen in Qualtrics when they're taking that survey. And so as a person says, yeah, I don't want to help my gay friend get married because maybe it's illegal or maybe I think it's wrong or something like that. But then the next option is mail a package, and then they want to like kind of let everybody know. But I don't hate gay people. I'm not anti-gay. And so they just go a little bit higher on all the other things. So the openly gay wasn't part of my experiment, but it sort of messed with things because people were so excited to help openly gay people do things. Actually, the atheist stuff worked out just fine for me, but I did another one later on with a control group so that I could compare differences to control groups. And I probably should have done that here instead of having openly gay. I should have put in a control group, but it's all right. It worked out okay. But just that's kind of what's happening, right? It's like people are like, well, I don't want to help that person get married, but I don't hate gay people, and so I really want to help them mail a package. And so then you get those weird kind of differences where people are significantly more likely. Generally, what you'd say is on these activities, on these tasks, there's really kind of no bias in the American system. You can plot it too. You can plot the difference, but the plot is sort of ugly, right? That's not an awesome plot, but. Okay, so that's the ANOVA. That's how to do it. I use these all the time in my research because I do experiments and I put people in various categories and I need to see like not just are they different, but by how much are they different. And so it's really helpful. So it's nice to be at the stage of statistics where we're doing things you're actually going to use in life. So keep at it. Good luck. I hope you're watching these videos.